Okay, can you see me now? Hear me now?
Yes, we can see and hear you.
Okay. Hi everyone. So I'm going to talk about the impact of temperature on heat capacity on ruthenium chloride at negative spin-spin coupling. So for a quick introduction, ruthenium 3 plus has only one unpaired electron in its 4d5 subshell. So the unpaired electrons in the RuCl3 2D lattice could be either collinearly oriented or arranged in the opposite directions or disoriented. So ferromagnetism arises when they are arranged in the same direction. So this equation, as shown in this equation, we can find the heat capacity by getting the derivative of internal energy over temperature. So moving on to the methodology, the input parameters should be set as shown in the screenshot here. So it is set to negative J. And first I selected the magnetic field of 0.001. The external magnetic field. So, and then the program was run on MATLAB and the graphical representation, the graphs were obtained. So after that, I set the B for the external magnetic field for 0.01 and 0.0001 and repeated the procedure. So these are the results I got. So here we can see at when the external magnetic field equals 0.001, we can see a very smooth variation of heat capacity to spin-spin coupling. Heat capacity versus temperature to spin-spin coupling. So we can clearly see that in the first graph that the temperature, the system does not accept heat the system does not accept heat at very low and very high temperatures. So as we decrease the external magnetic field by 10 times, we get narrower peaks, and the peaks are less intense too. So we can kind of explain this like this. So at minimum temperature, the spins are oriented in the same direction. So we can say it's an ordered state. And when we increase the temperature, the thermal energy, it overrides the spin-spin interactions and the magnetic interactions. So the system becomes disturbed and the coupling becomes irrelevant. So at a very high temperature, at infinite temperature, the spins are completely random and each spin will have a finite entropy. So the entropy will be a constant, which means the free energy of the system from which the heat capacity could be derived from becomes minimum. So when we increase the temperature, we can say that the heat capacity decays and plateaus with increasing temperature. So then just to compare with literature, I just shared this graph here from a paper I saw. So we can see that the peak intensity and the peak width decreases with decreasing B, the external magnetic field, at negative spin-spin coupling. I also included the relationships of energy and magnetization versus temperature for all three B values. So here we can clearly see that there's the phase transition occurs from here to here. It's a rapid, drastic increase in magnetization. The phase transition from ferromagnetic to paramagnetic occurs around 1000 to 1500 Kelvin approximately here. So the graphs of magnetization versus temperature and internal energy versus temperature for all three systems, they kind of compare. So these are the conclusions I drew from this procedure. The heat capacity increases upon increasing temperature and decays at very high temperatures. A smooth variation of heat capacity for external magnetic field 0.001. We could see that at there was a smooth variation of heat capacity for a negative spin for B equals 0.001, and also the peak width and intensity decreased with decreased B. And also we could see that the phase transition from ferromagnetic to paramagnetic occurred around 1000 to 1500 Kelvin.
Okay.
So I want to thank you. I want to acknowledge Professor Killian and the classmates for sharing their knowledge and guiding through the project. Thank you very much. And if you have any questions, you can ask now.
Yeah, thank you, Chameli. So, any questions in class? So we started uploading a little earlier than scheduled. Any questions on the line to Chameli? So I have a brief one. Can you please flip a couple of slides back? Yeah, sure. Forward, 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 forward. Can you please flip forward, forward, forward? Oh,
Here?
yes. So in your lower panels, why energy increases as you increase the temperature, and why it stabilizes near zero? Just how do you interpret it?
Near zero?
Yes. So you see your energy goes from minus 0.04 and then it approaches zero, right?
Yes.
So what happened? Why energy grows with temperature and why it approaches zero?
Because the entropy is released.
And can you explain it on the language of microstates? Like which microstate will be activated when temperature equals infinity?
So at minimum temperature, there's only one microstate.
Okay, and at maximal temperature?
I'm not sure.
Would you agree that it will be all microstates activated approximately equally?
Equally?
Yes. And half of them have positive energy, half of them have negative energy?
I can say that they are not activated equally.
Okay, but there will be a larger number of states activated. So in first, John agrees. He is nodding to this. Can you please comment how you just help Chameli your view on this?
I think that as you increase the temperature, I guess in this case up to 4,000 Kelvin, the distribution of state probably approach something fairly symmetric. So everything of negative energy values would cancel out with everything of positive.
Chameli, what do you think of this statement by John? Does that look realistic?
It makes sense, yeah.
Okay. More questions to Chameli? Yes.
On the graph that you're currently showing, and in your table in your project, you show that there is.
Yes, this is fine.
Can you explain? Yes. Can you explain the spike in magnetizations at approximately 500 Kelvin, or B is equal to 1,000? Top half.
Is that at the ground state?
Then, if it is, can you explain why it decreases for a weaker value of B?
Dr. Kilin, I cannot hear properly. Could you?
Sorry, I will talk louder. So in your on this slide, at B is 0, 0, 1.
0, 0, 1, okay.
On your magnetization versus
Yeah.
graph. You have a spike before
Yes.
the curve, and
Yeah.
you have a similar spike on the B is 0, 0, 0, 1, and no similar spike on 0, B is equal.
Oh, yeah. Now I get it. It's probably. I'm sorry. I cannot give an exact answer because I'm not sure about it.
You can try it and maybe start thinking in the direction whether the spikes will stay here or disappear if you increase sampling of microstates. If you use more than 20,000 microstates.
And Dr. Kilinska, will you agree with the statement that this is an artifact of the limited number of calculations we have performed?
So let me help so we can go forward. John, can you comment on this? Okay, so we used a limited number of microstates, right? And sometimes they're not sufficient to represent a realistic situation. So especially the peak in the magnetization can be shown not maximal, not -16, but something bigger, if the procedure that John has described failed to find the ground state. So for insufficient number of trials, ground state was not found, and it gives this numerical error. Chameli, does it sound realistic to you?
Okay. Okay.
Steven, does it sound realistic to you?
Yes.
Okay. More
Thank
questions. More questions to Chameli? 1, 2, 3. If no, let's thank